Cool. Welcome back. Goal for today is see if we can wrap up any questions with project 3 and then hopefully move into module 4 by Wednesday. How's it going so far? Good quiet? I'm trying to remember from Friday, because I know Friday we spent a lot of time kind of troubleshooting some individual work. So let's just restart. I think we had gone over like setting up the function that we needed at least to start. And overall goal is kind of like make sure that we can set up a function where we know the solution. That gives us a verification step where we can compare to an actual function that we know, and then move on to like adding all the other stuff that we want. Like we want to include drag, we want to include gravity, make it slightly more realistic. Like maybe there's other things that we would want to in the future, but this is the general process. Start small, just the basics. At least, I mean, it's still rocket science. It's not like basic and easy. Basic is in solvable, even if we're not creating the solution ourselves. And then, so if you like numerical methods, or you just want to like try a different way of integrating these problems, Solve IVP has a lot of built-in methods. Some are explicit, some are implicit, and they work really well. So if you want to try something new, Solve IVP is a great way of using like more of the industry standard. Like if you have differential equations, Solve IVP is the thing that you would use to integrate them in general. In MATLAB, it's like RK345 and RK23. Those are usually the things that you start off with. And then if those don't work, then you move to like RK23S and 45S, but different kinds of Runge-Kutta methods. So I'll try importing that. The setup is a little different. I mean, it's the same general kind of process that we've been using. You define, time is defined. It's some like range of values. In here, I want to define it from 0 to whatever final time. So that's giving it a range of time to solve for. This first line is my differential equation. In general, differential equations are functions of your state. Your state can be as big or as small as it needs to be. It can have one value in it. It could have 300 values in it, as long as the function f of t and y returns the derivative of all 300 values. In this case, we only have 3, so we'll give it 3 values. We'll get 3 derivatives. That's all we need. And then in a lot of our like integration methods, when we were like looking at Euler step or Hune step, any of those, we would set up the initial values as like state. The state of row 0 is this. Here we just give it that first row, and it's going to fill in the rest of the details for us. So once it knows how much time we need and what the initial values are, then it can go and solve. An optional thing that you can do is say, I want to evaluate at these points in time. So if I want to look at 50 points in time, then I can give it a value of like a lin space that way. And usually helps to just at least see, is it giving me something that makes sense? sol.t is going to be the solution time points. sol.y is all of my states, position, so height, velocity, and position. 0 is going to be just height. So now I could look at height as a function of time. And I get 0, which was my initial condition. Makes sense. The slope is 0, so the change in height at time 0 was 0. Also makes sense because my initial velocity was 0. And then it starts ramping up, like flying away up to 600 meters. Not bad for a little rocket. And I mean, we're ignoring gravity and drag, so we're like launching this out of the space station or something. Still pretty good. So now I want to compare it to that Tsiolkovsky solution. A lot of consonants in here. Let's do that first. And at face value, the answer to this differential equation is saying that mass and speed, there's a one-to-one function. So if I can plot mass and speed on either axis, I should be able to create a function that is the same thing. Whether I define Lin space of masses or I use mass, but I should be able to use either mass or speed to figure out the other one with a one-to-one function. Here it's in the exponential form because that's like how this function kind of works out. So I plotted that. So mass and speed looks like this. Kind of reading backwards. Initial mass was 250 grams. Final mass was 50 grams. So at that final mass, I was 400 meters per second fast. So speed versus mass. The more mass I lose, the faster I go. Now let's compare that to, I'll use the same x-axis, so that mass, and I can define my own mass. Like I could just call this m. Say m is a Lin space from 0.05 to 0.25. Make, I don't know, 50 values along the way. Let's go 100. Why not? And then plot that negative u log of m over m0, just solving for speed instead of solving for mass. And sure enough, this red line goes right through every one of my numerical points. And at this point, it's like a big check in my to-do list box of numerical methods. I've verified my result, that I can use numerical methods to do anything that you can do by hand. That's what, at least for this case, for rocket science, I know that my numerical methods are creating things that I have already seen solutions for. That's good. That means that I can start doing more complicated stuff and not worry about how the numerical methods are like converging, and are there other things happening? Am I still conserving energy? We're good to go. but it should work. It should work. It doesn't always work the way we want, but it's nice when it does. This one, what we should find is that speed and layers are not a function. I mean, they are functions of time, but they function from each other. You can see it now. Oh, just make another plot. Yeah. This is these two are no, truly can't say that. So like when I get I solve for the VF in terms of So I saw like a little bit of people getting into adding gravity and drag for the rocket, like when you're trying to solve the actual like rocket equation. There is gravity, there is drag. It's going to change how the solution kind of works out. And for the most part, like at this step, we're trying to make sure that integration method doesn't matter, whether it's implicit or explicit. So here I've got like both an implicit and an explicit kind of plotted. I can't tell the difference between the two. They're both giving me the same answers, but they're not matching my original like Tsiolkovsky kind of logarithm function. Some people would just say like, so one thing you can do is like, okay, my integration works. I'm okay with the mismatch because now it's more realistic, so it can't match the ideal solution. That's perfectly fine. Like, it's a check in the box. We can move on. Others might say, well, there's got to be a way that I can reproduce that yellow curve with this function, even with gravity drag. And the way to do that is our dm dt. The bigger that mass rate is, the less important gravity and drag become. So right now it's like 50 grams per second. I can make it like 5 kilograms per second. It's really going to change, like it's only going to solve for a quarter of a second, but it'll now thrust is a lot bigger for a lot shorter period of time. So I could make that 1,000 times bigger and look at the plot, and sure enough, I get everything lining right up on top, right on top of each other. And now that things are kind of lined up, I could look at, all right, so then what are the errors of these things? Like take the Tsiolkovsky and add it to those two solutions, or subtract, however you want to think about it. And then I can start looking at like more detailed, like which method is better for my solution, right? And again, both of them about the same, like not for all the initial mass values, there's basically no difference. And then as we start getting to the really small mass values, there's small differences, but roughly same amount of error, like which is kind of what we'd expect for most of these integration methods, like whether it's implicit or explicit for this kind of thing. It's not a huge deal. I guess the only benefit to the implicit, these like red circles, is the error seems a little more predictable. Like it's always proportional to how much mass you lost somehow. It's not as much like oscillating and changing. And that, yeah, if you want to do that step, then you're welcome to. But if you're happy with numerical methods converge, I already showed that I can match that log function, and that's fine. It's up to you. Also, I guess it's like time investment. Like this is what I want to do with my time versus how can I minimize time spent on project, maximize goal return value. But just in case you're seeing this thinking it's wrong, or maybe that it's right, or yeah. still describing differential equation. The change in time is maybe, and it's just, we already know how to solve that differential equation, but still, but we're going to use that mass and time state and other acceleration. So one way that we could do it is only have velocity acceleration at those two state, or sorry, position and velocity state. And then mass is now a function of time. Time. The state can be Yeah. So usually my general kind of bookkeeping goes into numerical measure values of markers to show that these are discrete values. I don't have a continuous connection between, and then functional like that lines. I might not evaluate it at this time, but there's a function. Coming back up here. Here, let's grab. So my general, I'm gonna say that it's common practice, but talk to 3 different people. They all have a different common practice, but here's my common practice that I recommend you to implement and kind of stick with. Is that when you have like discrete values, like you're integrating a function, I don't have anything between these 2 data points. Like these 2 squares, I know I can interpolate between them, but there's no actual like numbers that I have between them. So I like to keep track of that by drawing like squares, like discrete data points for those. And then whenever I have a function, like an actual like f of x, or in this case, it's a log of mass. If I know the log of that current mass to the initial mass, then I have like a continuous function describing that. That one I like to use a line because I know, because there are actual, I can get further and further closer to this line and evaluate more and more points. It's just a continuous function. So that's my recommendation. If you have measured data points or you have integrated states, like steps in time, use some kind of marker to say like these are discrete data points, versus functions, like if you're plotting sine of x, just a straight line. Like it's a continuous thing, so you can always make the line smoother and smoother and smoother, no matter how close you zoom into it. That's my recommendation as a good common practice. But again, you'll go work for some other engineering firm and they'll say integration is a line and something else is a data point. It's like, I don't know, choose your battles. But I'm not going to fight you over it, but I think it's a good bookkeeping practice. Let's see, so we got rocket defined, have that solve IPP. So once we have like our, if we speed run through this thing, verification step, check, done. My simple rocket equation produces exactly what my Tsiolkovsky friend had created. And then coming down, create a rocket, make it more realistic, compare two different integration methods on this now, like gravity and drag. They both agree with each other. Okay, great. Moving on to the next step. I want to know how do I pick DMDT such that this graph goes from 0 and at the final time, which is going to change because the faster I burn, the less time I have. The slower I burn, the less height I can get to. But well, not always, but anyway. So right now I'm at like 430 or 440 meters high in 4 seconds. So I want to change that DMDT, but I want to use a route finding method to get there. So I want to define a function where the output is this value, that 430 or whatever it happens to be, minus 300. And if I can get that to 0, then I have the right DMDT. All right, so now I need get rid of that. Mod secant. That one's defined. I think I deleted my FDM setup. So I'll copy this back in there. So my input is DMDT. I'm giving it some default values for M0 and all that. And my work, I already did the work. Like I know how to get to this thing. I just want to copy it and put it inside of a function. So I'm going to come back up. In order to create like this height versus time graph, I need that solution. I'm going to use implicit method. I could use whatever I want. But to start, let me just like copy everything in there. Make sure it's all tab corrected. I don't want to overwrite DMDT because that, I'm going to zoom out a little so I can see everything. DMDT is my input, so I don't want that to be defined inside the function. Otherwise, it's going to overwrite whatever hard work I just put in there. So get rid of this. And I'm going to say that it's DMDT equals DMDT. That I'm change whatever input I give at the top, 0.05, 500, whatever, 500 kilograms per second. U, again, that's an input. I don't want to overrate my inputs. Get rid of that. T, right now it's lin space from 0 to something. Really, all I need is a final time, right? So I'm going to delete all of this and just say my final time is however long it took to burn that mass. And then instead of using a T-1, I'm going to call that like TF. And I don't need to evaluate this at multiple points in time. All I need is that last point in time. Oh, I'm going to use SOL. Oh, yeah, let's do this. So I don't need this one. I'm going to use that Redal method. No like particular reason, just, and then I'll define my error. Take my first state, last value, so -1 is the last value, and subtract 300. Let's double check that we're actually getting what I thought we should be getting. So I get 125 because the last state that I had just calculated was 430-ish. So subtract 300, now I get 130-ish. I was just looking at a graph, so here I'm getting the exact value. It's good, seems good. Oh, make sure that this is actual DMDT, because that's my input is DMDT, not DM. So just making sure that things are going to work the way that I want. So then I'll come back up, check one more. So let's go up to like 1 kilogram per second. Changes my integration curve, and I can look at how high I get. Roughly I'm getting to like 30 meters, because everything's 1 kilogram per second. I'm setting off like a small bomb. I mean, it still gets pretty high because things are moving fast. And then I don't need to redefine it, but so 30 meters minus 300 should get like a negative, I'm 270 meters away, and that's what I get, negative 270. So if this function is evaluating the height correctly, which it seems like it is, then the next step is I need to find like the root of this function. That if I plug in the right DMDT, this function will give me 0. Then I've solved the problem. I'm now a rocket scientist. Hooray. Fire. But yeah, once you have stuff that works, like you don't need to like reinvent the wheel, like repeating everything. Copy, paste, and kind of trim it down, which is exactly what I did. I knew that the code that I was using before worked in the first couple of steps. Now I can just trim it down to like just the bare bones to get that function to do what I want it to. Any last questions? We have like 1 minute left. Professor Cooper, ink search isn't working for me. Oh man, are you getting an error? Yeah, it's giving this weird error in the ink search. Oh man, let me help with that. That one's, we should be able to fix that. Ink search. Yeah, that might give us an error. I know that it will give you an error. That's why I'm like trying to help out here with the questions. All right, so I have ink search. I just copied it in. I know how to run it. At least I know how to put inputs into it. Ink search, FDM. So that's my function. Let's start off. I know 0.05 was not big enough. 1 was too big. So let's try like 21 steps between those values. Then it gives me this weird index error that it can't index to a scalar variable. It's like, what are you talking about? So kind of tracing my way back through this. It's saying that it happened when it tried to do this. Let me make sure that I'm, yep. And it happened somewhere in here along this line. I'm surprised it's this line. I didn't think it would make it past here. Yeah, I'm surprised it made it to there. I don't know how it made it to there. But anyway, the main problem is that we want to evaluate this function with one dmdt at a time. So I can't say f equals func of x. I have to say f is going to be an array where I'm going to take x, split it into xi's for xi in x. And now when I run it, at least I get an output. It's not, I don't get a good output, but no brackets found. So there's something wrong. Maybe it's something wrong with my FDM so far, but at least I'm getting outputs. It's the error goes away. So that's the trick there. Is that make sure you're only plugging in one dmdt at a time in that function evaluation. Cool. All right. Thanks a lot. See you again on Wednesday.